San Andreas. Before 1906, there were more than 11 major earthquakes in 75 years.
We call it the big one because we expect the next San Andreas earthquake to be in the upper magnitude 7s to a magnitude 8.
The big one. When California moves again. The real question isn't whether California will face another major earthquake, it's when. Because deep beneath the state's cities and highways, forces powerful enough to reshape entire landscapes are still at work. To understand why scientists remain so concerned, we need to look at the crack that built California itself. Chapter 1. A disaster hidden in plain sight. Most natural disasters can be seen coming. A hurricane appears on satellite images, a wildfire climbs a hillside, a tornado forms beneath a darkening sky. Earthquakes are different. There is no warning on the horizon, no visible approach, no sign of what is about to happen. The danger exists long before the shaking begins, hidden deep underground, beneath cities, schools, hospitals, power plants, and ports. California's earthquake risk is not a mystery. In many ways, it is one of the most studied natural hazards on Earth. Scientists know where the major faults are. They understand how tectonic plates move. They know large earthquakes have happened before and will happen again. The challenge is timing. The forces involved operate miles below the surface, beyond direct observation, yet their fingerprints are everywhere. Mountains have risen. Valleys have shifted, rivers have changed course, entire landscapes bear the scars of ancient earthquakes. California itself was shaped by movement. The ground beneath it never stopped changing. The question is not whether the Earth is moving, it is. The question is what happens when centuries of stored energy are released in less than a minute. Chapter 2. The crack that built California. The San Andreas Fault stretches roughly 800 miles across California. It is one of the most famous geological features in the world. From the air, parts of it resemble a scar running across the landscape. It cuts through mountains, crosses deserts, slices through farmland, and passes dangerously close to some of America's largest cities. But the visible fault is only a small part of the story. The real action takes place underground. The San Andreas marks the boundary between two massive tectonic plates. To the west lies the Pacific Plate, to the east lies the North American Plate. Neither plate is standing still. The Pacific Plate moves northwest relative to North America at roughly 2 inches per year. That may sound insignificant. It's about the speed at which human fingernails grow, but geological time changes the scale of everything. Over a century, that movement becomes more than 16 feet. Over 1,000 years, it exceeds 160 feet. The problem is friction. Imagine 2 enormous sheets of sandpaper pressed together. As you try to move them, they don't slide smoothly. They catch, they lock, pressure builds. Then suddenly, they slip. The San Andreas behaves in much the same way. For decades or even centuries, sections of the fault remain locked. The plates continue trying to move. The rocks resist. Stress accumulates. Eventually, the rocks can no longer withstand the pressure. The fault slips, and energy that took generations to build is released in seconds. That release becomes an earthquake. Most of the time, California appears stable. Cities grow, roads expand, businesses open, families move into new neighborhoods. Yet beneath all of it, the process never stops. The fault is moving right now, slowly, relentlessly, exactly as it has for millions of years. Chapter 3. The earthquake. Most people forgot. When people think about California earthquakes, they usually think about San Francisco. 1906. The images are iconic. Collapsed buildings, twisted streets, a city in flames. But nearly 50 years before that disaster, another giant earthquake struck California. Today, most people have never heard of it. On January 9th, 1857, a massive rupture tore across the southern San Andreas Fault. Researchers estimate the earthquake reached approximately magnitude 7.9. The rupture extended nearly 220 miles. In some locations, the ground shifted more than 30 feet. Streams changed course, trails no longer lined up. Entire sections of landscape were displaced. The earthquake became known as the Fort Tejon earthquake. What makes it remarkable is not only its size, it's where it happened. In 1857, Southern California looked nothing like it does today. Los Angeles had fewer than 5,000 residents. There were no freeways, no container ports, no airports, no sprawling metropolitan regions stretching across multiple counties. The fault was essentially the same. Everything built on top of it was different. As a result, the human impact remained relatively limited. Had the same earthquake occurred today, the consequences would be measured on an entirely different scale. For geologists, Fort Tejon remains one of California's most important earthquakes. Not because it was unusual, but because it proved something critical. The southern San Andreas Fault is capable of producing enormous ruptures. This isn't speculation. It isn't a worst-case scenario invented by emergency planners. It happened before, and the evidence is still visible more than 160 years later. The Earth remembers, even when people forget. Chapter 4: The Day San Francisco Changed. By the early 20th century, San Francisco had become one of the most important cities on the American West Coast. Its harbor connected the United States to Asia. Its economy was booming. Its population was expanding rapidly. Few residents understood how close they lived to one of the most active fault systems in North America. Then came the morning of April 18th, 1906. At 5:12 a.m., the ground began to shake. At first, some people assumed it was another minor tremor. California was already familiar with earthquakes, but within seconds, it became obvious that this was something different. Buildings swayed violently, brick walls collapsed, streetcar tracks twisted, church towers crumbled into the streets. Across Northern California, the rupture raced along nearly 300 miles of fault. Scientists now estimate the earthquake reached approximately magnitude 7.9. The energy released was enormous, but what happened next proved even more destructive. Gas lines ruptured, fires ignited throughout the city, water mains broke, leaving firefighters unable to contain the flames. For 3 days, San Francisco burned. Entire neighborhoods disappeared. Thousands fled carrying whatever possessions they could save. Families slept in parks. Smoke filled the sky. Historic photographs show block after block reduced to rubble. One surprising fact often goes unnoticed. Many deaths associated with the disaster were not caused directly by the earthquake itself. They were caused by the fires that followed. In some neighborhoods, the shaking ended in less than a minute. The destruction continued for days. More than 28,000 buildings were destroyed. Hundreds of thousands lost their homes. For Americans, it was one of the first demonstrations of how devastating a major earthquake could be. For scientists, it became a turning point. Researchers studying the disaster developed what became known as the theory of elastic rebound, the idea that faults slowly accumulate stress before releasing it suddenly during earthquakes. More than a century later, geologists still study the 1906 rupture, not because it was unique, but because it revealed how the Earth behaves when generations of stored energy are released all at once. Chapter 5: The Place Where You Can See the Fault. Most earthquake faults are invisible. They lie hidden beneath cities, forests, rivers, and layers of sediment accumulated over thousands of years. The San Andreas Fault is different. In one remote corner of California, the fault reveals itself with remarkable clarity. The place is called the Carrizo Plain. At first glance, it doesn't seem extraordinary. Dry grass stretches toward distant hills. Dust drifts across open terrain. The landscape appears empty, quiet, almost forgotten. Then you begin noticing things that don't quite make sense. A stream suddenly changes direction. A ridge appears offset. A dry creek bed seems disconnected from itself. The farther you look, the stranger it becomes. It's as if someone grabbed the landscape and shifted part of it sideways, because in a way, that's exactly what happened. If an alien civilization arrived on Earth and asked geologists where earthquakes happen, this is probably where they would bring them. Few places on the planet make plate tectonics easier to see. Researchers often describe the Carrizo Plain as one of the world's greatest natural laboratories. Some of the displaced features visible today were created during the Fort Tejon earthquake of 1857. More than a century and a half later, the scars remain. Not because the Earth stopped moving, but because the movement was so large. Standing in the Carrizo Plain changes how many people think about earthquakes. The San Andreas stops being a line on a map. It becomes something physical, something real. A reminder that tectonic plates are not abstract scientific concepts. They are enormous sections of Earth's crust, and they are moving right now. Chapter 6. The section that keeps scientists up at night. If there is one part of the San Andreas Fault that attracts extraordinary attention, it is the southern segment. This section extends from the Salton Sea towards some of the most densely populated regions in North America. What makes it concerning is not recent activity, it's the absence of it. For centuries, parts of the southern San Andreas have remained unusually quiet. That might sound reassuring. To many geologists, it isn't. One of the biggest misconceptions about earthquakes is the idea that faults become safer the longer they remain inactive. Scientists don't necessarily see it that way. Sometimes silence is exactly what attracts attention. To understand why, researchers turn to a field known as paleoseismology. Instead of studying earthquakes directly, they study the evidence earthquakes leave behind. Scientists dig trenches across active faults. Layer by layer, they examine sediments deposited over hundreds or even thousands of years. Each layer contains clues, broken deposits, shifted soils, fragments of ancient landscapes frozen in time. Together, those clues form a record of earthquakes long before modern instruments existed. The evidence suggests that parts of the southern San Andreas may not have experienced a major rupture for more than 300 years. That does not mean an earthquake is overdue. Nature doesn't operate on schedules. Faults don't follow calendars. A quiet fault is not a countdown timer, but it does mean scientists pay attention, because while nobody knows exactly when the next major rupture will occur, researchers know what this section of the fault has done before. And what it has done before was enormous. Some of the earthquakes recorded in the geological record occurred before the United States existed. Others happened long before California became home to tens of millions of people. The concern isn't based on speculation, it's based on evidence written directly into the landscape itself. And that evidence tells a consistent story. This fault is capable of producing very large earthquakes. The question is not whether it can, the question is when it will. Chapter 7. What scientists really mean by the big one. Few geological threats have become as famous as the big one. The phrase appears in movies, television shows, news headlines, conversations between neighbors. For many people, it has become synonymous with California itself, but among scientists, the term is surprisingly controversial. Many researchers avoid using it entirely, not because the threat isn't real, but because the phrase creates a misleading impression. It sounds precise, as if scientists are talking about one specific earthquake, one exact magnitude, one known location, one inevitable event. The reality is much less certain. There is no official definition of the big one, no universally agreed upon magnitude, no single earthquake that everyone is referring to. Instead, the phrase usually describes a scenario, a very large earthquake occurring on a major section of the San Andreas Fault. Most planning exercises focus on a magnitude 7.8 event. That number may not seem dramatically larger than a magnitude 6 earthquake, but earthquake scales are deceptive. A magnitude 7.8 earthquake releases hundreds of times more energy. The difference is not incremental. It's enormous. Yet here's something even more surprising. Some scientists argue that the greatest danger isn't the earthquake itself, it's the systems modern society depends on. Electricity, water, transportation, communications, supply chains. A city can survive a minute of shaking. Recovering from weeks without critical infrastructure is often far more difficult. And that's what concerns emergency planners most. Not simply whether buildings remain standing, but whether society continues functioning afterward. Chapter 8. If it happened tomorrow. Imagine it starts at 8:17 on a normal weekday morning. Freeways are full, schools are open, hospitals are operating, millions are commuting, everything seems routine. Then the fault ruptures. At first, people think it's a passing truck or a small tremor. Seconds later, the shaking intensifies. Traffic stalls, windows explode, power lines whip through the air, water mains burst beneath the streets. Emergency centers are flooded with calls. Millions reach for their phones and discover the network is overwhelmed. For years, scientists have studied what a major San Andreas earthquake could do to modern California. The best-known effort, the shakeout scenario, modeled a magnitude 7.8 event on the southern San Andreas Fault. The results were alarming: thousands injured, thousands of fires, severe infrastructure damage, and massive economic losses. But researchers stressed one crucial point: these were not predictions, they were warnings. The goal was never to forecast the future, it was to expose weaknesses before disaster strikes. Again and again, the same lesson emerged. The earthquake is often only the beginning. The shaking may last less than a minute. Recovery can take months or years. Roads must be repaired, water restored, power rebuilt, supply chains restarted, communities reconnected. Large earthquakes are not just geological events, they become infrastructure crises, economic crises, human crises. That is why preparation matters long before the ground starts to move. Chapter 9. Why we still can't predict earthquakes. After every major earthquake, the same question is asked: why didn't scientists predict it? It's a reasonable question. We can forecast hurricanes, track storms from space, and predict solar eclipses centuries in advance. So why not earthquakes? Because earthquakes begin where we cannot see. Miles beneath the surface, immense pressures build within rock formations hidden from direct observation. Scientists can map faults, measure ground movement, and estimate long-term risks, but they cannot watch a fault rupture before it happens. That distinction changes everything. California operates one of the world's most advanced seismic monitoring networks. Thousands of sensors, GPS stations, and satellites constantly measure the Earth's movements. The data is extraordinary, yet despite decades of research, no scientifically reliable method can predict the exact day, hour, or minute of a major earthquake. Scientists can often identify where an earthquake is likely. Sometimes they can estimate how large it may be, but they still cannot answer the most important question: when? As a result, the goal has shifted. The focus is no longer prediction, it is preparedness. Because waiting for certainty is not a strategy. Preparing for uncertainty is. Chapter 10. The few seconds that could save lives. Although prediction remains impossible, warning has improved dramatically. The distinction may sound small, it isn't. California's Shake Alert system represents one of the most sophisticated earthquake warning networks ever built. The system works because earthquakes travel at different speeds. When a fault ruptures, the first waves that leave the source move quickly but usually cause limited damage. The strongest shaking often arrives seconds later. Those few seconds create an opportunity. The moment an earthquake begins, sensors nearest the rupture detect it. Computers analyze the incoming data almost instantly. Alerts are then transmitted to regions that have not yet experienced the strongest shaking. Sometimes the warning lasts 10 seconds, sometimes only 2 or 3. Occasionally there may be no warning at all for people closest to the epicenter, but even a few seconds can matter. Engineers call it protective action time, enough time to slow trains, pause delicate surgical procedures, open fire station doors, shut down sensitive industrial equipment, move away from heavy machinery, step back from glass, or simply remember one of the most important earthquake safety instructions ever developed: drop, cover, and hold on. The system cannot predict earthquakes. It cannot tell anyone when the next major rupture will occur, but it can provide something that previous generations never had: time. And during a major earthquake, time can be the difference between injury and survival. Chapter 11. The Earth is still moving. The most unsettling fact about California's earthquake risk is also the simplest. Nothing has changed. The same forces that caused Fort Tejon in 1857 and San Francisco in 1906 are still at work today. Beneath cities, highways, and millions of ordinary lives, the Pacific Plate continues to push. The North American Plate continues to resist. Stress is still building. Most of the time, nobody notices. Life goes on. Schools open. Businesses operate. Traffic fills the freeways. Entire generations pass without experiencing a major earthquake. And that creates an illusion that the ground is permanent, stable, finished. But California was never finished. It is still being shaped by forces deep beneath the surface. Tonight, the Pacific Plate will move another tiny fraction of an inch. No one will notice. The movement is too small, too slow, too quiet. But geological time has never followed human schedules. The Earth does not stop moving simply because we stop paying attention. And one day, whether years from now or decades in the future, California will feel that movement again. Not because anyone can predict the date, not because disaster is guaranteed, but because the process that created California never stopped. The fault is still there, the plates are still moving, and the Earth is still writing the next chapter. Outro. For most people, earthquakes exist as brief moments in the news. A few headlines, a few days of coverage, then life returns to normal. For geologists, the perspective is different. They think in decades, centuries, sometimes millennia. From that perspective, every major earthquake in California's history is part of the same ongoing story. A story written by moving continents, stored energy, and forces far larger than any city built above them. The next chapter has not been written yet. Nobody knows exactly when it will begin. But deep beneath California, the process is already underway, quietly, patiently, exactly as it has been for millions of years. And one day, everyone will notice. If you enjoyed this documentary, subscribe for more deep dives into science, geology, history, and the forces that shape our world. And if you live in an earthquake-prone region, let us know in the comments. Have you ever experienced a major earthquake? Thanks for watching.